We've already looked at finding the shortest path through a network. In some situations, we may need to find the longest path through a network. For example, we may want to find the maximum distance to travel past the most houses. We may want to maximize profit. Or, in a video game, we may want to collect the most points. In this video, we're going to have a look at what the longest path is. We'll look at how we can find the longest path. And we'll look at an algorithm for finding the longest path. Of course, we'll look at a couple of examples. A longest path problem is a problem where we must find the longest path between two nodes in a network. It's not always the longest distance. The longest path problem includes maximizing profits or the number of points collected. Clearly, we cannot backtrack in a longest path problem, otherwise we could continually go to and fro between nodes to increase the length forever. We can therefore only find the longest path if the network is directed or if we're not allowed to return to previous nodes. In my number of paths video and shortest path video, we looked at this network. Imagine if you were paid to hand out pamphlets or brochures and you wanted to maximize the number handed out on the way to work. You would want to take the longest path or the path with the most houses or businesses. In this example, we traced the number of paths and added them up. The longest path was A. This process would become tedious as the network became larger and more complex. In this case, we can use an algorithm to find the solution. Unfortunately, we cannot find the longest path by simply changing the minimum to a maximum in the Dijkstra's shortest path algorithm. There are other more complex algorithms that we can use, but in this video, we'll follow this simple procedure. Step 1 is to label the starting node 0. Step 2, we find unlabeled nodes that are only accessible from the nodes that are already labeled and label them with the maximum length possible. Step 3, we repeat step 2 until you've reached the finishing node. And in the final step, we backtrack through the nodes to establish the longest path. This is the same network we previously found the shortest path for. This time, we're going to find the longest path from A to O using the algorithm. So we label the starting node 0, and we find unlabeled nodes that are only accessible from the node that's already labeled. These are B and F. And we label them with the maximum length possible from the previous node. That's 2 for B and 1 for F. Now find unlabeled nodes that are only accessible from nodes that are already labeled. We'll start with C. This can only be accessed from B, so we add 3 to 2, and we get 5 for C. The next one is G. This is accessible from B and F. If we traveled through B, we'd get 5. If we traveled through F, we'd get 3. So we label it with 5, which is the maximum length. Now we move to K. This can only access from F, so we add 4 to 1, and we get 5 in K. We repeat this process, finding unlabeled nodes that are only accessible from the nodes that are already labeled, and label them with the maximum possible length. So D can only be accessed from C, so we add 5 to 5 is 10, and H, go 5 plus 6 is 11, which is greater than 5 plus 3. And we continue this process, and we label all of our nodes with the maximum possible length. Once we get to O, we've completed the network. Now we need to backtrack through the nodes to establish the longest path. To get to 19, we had to add 4. So we go back to 15, or node J. Then we take 3 from 15 and we get 12. And we continue this process until we get back to the starting node. Working backwards, we got O, J, E, D, C, B, A. Therefore, the longest path is A, B, C, D, E, J, O in this network. Let's find the longest path from A to G in this network. First, we assign a value of 0 to the starting node. Now we find unlabeled nodes that are only accessible from the node that we've already labeled. The first one is B, so we'll label it with 4. The next one is C, so we label it with 9. Once we get to C, we can go to E or B. So if we go to E, it's going to be 11. If we go to B, it's going to be 9 plus 4, which is greater than 4. So we cross out 4 and we write 13 for B, because that's the maximum path to get to B. Now we look at nodes connected to B, and we go 13 plus 15 is 28. To get to D, we could go to D from B or F. If we add 11 to 13 to D, we get 24. But if we add 5 to 28, we're going to get 33. So we're going to go through F to get to D. From F, we can also go to G, so we'll label that as 35, which is 28 plus 7. But we're not finished yet. We've got to go back. So from D to get to C, we could have gone 33 plus 6, so we cross out 9 and go 39. And then from C, we can go to E, so 39 plus 2, so we cross out 11 and write 41. This time from E, we can go to G, so 41 plus 16, we cross out 35 and we were up 57. Now we finished it, we've got to backtrack through the network to find the longest path. So 57 take 16 was 41, take 2 was 39, take 6 was 33, take 5 is 28, take 15 is 13, and then we took 4 and we went back to C, so we visited C twice, and we take 9 to get back to 0. So when working backwards, we got G, E, C, D, F, B, C, A. So the longest path is from A, C, B, F, D, C, E, G in this network. In summary, in this video, we've had a look at what the longest path is, we've found the longest path, and we've used the longest path algorithm. Thank you.